So friction that we came in last lesson, we came up with the idea that friction was equal to mu r when it was its maximum value, where mu was the coefficient of friction and r was the normal reaction. So if you weren't here on Tuesday's lesson, you need to be paying extra special attention to this bit, because the maximum value that the friction can take is mu r that we've just written there. So I've said we're looking at statics still. We'll eventually do a different exercise that's on dynamics with things moving, and this time we're going to include friction, and then we'll be bringing in some things to do with connected particles as well. Sorry, my mind went blank there. So I've said earlier we saw that the frictional force F was less than or equal to mu r. In other words, that was the maximum thing that it could be, but it didn't have to be that maximum value. It could have been less than that. Where F is equal to mu r if the object on the plane is moving. Or what else could be true when F is equal to mu r? It could be moving, or on the verge of moving, or on the point of slipping, or in what kind of equilibrium did we call it? Limiting equilibrium. There's a few different ways we could say that. So where the object is not moving, we saw that the force of friction acts in a direction opposite to that which it would be moving if the frictional force wasn't there. Now that sounds a bit confusing, but it's just saying if something was about to move, if something was on the point of slipping down the plane, the frictional force would be going up the plane. It's not actually moving down the plane, but if it was going to move down the plane, the friction would be up. If it was just moving, if it was about to go up, then the friction would be down. So we've just got to be carefully thinking about that idea of which direction friction goes in. So hopefully keeping up with writing the notes for these things as well. It says a box of mass 8 kilograms rests on a rough horizontal plane. So it's at the moment it's not moving, and it's on a rough horizontal plane. The coefficient of friction between the mass and the plane is 0.5. Find the magnitude of the maximum force P which acts on this mass without causing it to move if the force P is horizontal. So this is quite a simplified problem to begin with because it's just on a flat surface, and we're obviously going to be doing some more complicated ones that aren't on flat surfaces. The first thing it wants us to deal with is if the force P is horizontal. So I'm just going to pretend we're only looking at that scenario. So we have a flat surface, not that that looks particularly flat, and I want to add on some things. So I know it's got its normal reaction, and I know it's got its weight of 8g. And there's the coefficient of friction, which is 0.5. And there's a force, which is going to be pushing it along P. Now, it's asking for the maximum value of P. But it says we want it to be the maximum value without causing it to move. So what type of scenario will it be in if it's the maximum value that P can be?
Limiting equilibrium.
It will be in limiting equilibrium. It's going to be at its very, very maximum before it starts moving. And for a flat surface, this is dead easy. But if it was on a sloped surface, it's a bit trickier just because we've got a lot more forces happening. So because it's just about to move, we know that it is in limiting equilibrium. And we know that the force coming on this side is the friction, which we can just say is mu r. So a nice simple problem that we've got here. Very quickly, we can say that r is equal to 8g. And because it's in limiting equilibrium, P is equal to mu r, which is 0.5 times 8g, which is 4g. So the maximum size that P can be is 4g. What's the minimum size that P can be
Same thing.
for it not to move?
Oh, no, the same thing. It's limiting.
No, because it doesn't say it has to be in limiting equilibrium. It just says what's the smallest thing that P can be just so that it doesn't move. Zero, yeah. P doesn't have to be there, and it wouldn't move. So if P was anything, this is not the question, but if P was anything between 0 and 4g, it would not move, okay? Because sometimes they might ask you to do an inequality. They might say, what is the range of values of P so that the block does not move? So I could say this. But I'm not asking for that in this question. So I'm actually just going to leave that off here. And if you get a nice answer like 4G, you can actually leave it as 4G. You don't necessarily need to put that into decimal if you don't want to. Okay, part B of the question is a bit different. It says the force P now acts at an angle of 60 degrees above the horizontal. So it's now acting like this, where this is 60 degrees. And we've got R, we've got mu R, and we've got 8G. Has anything, I don't know how to say this without giving the answer away. So are we just going to say, instead of P being equal to mu R, can we just say, I'm actually not going to do it, it's going to be more confusing. First of all, what do we need to work out in this situation then?
P cos 60, P sin 60.
Okay, so we'll add that onto the diagram that we're going to have a P cos 60 and a P sine 60. What would you then do next, Muhi?
Before you did R equals 8G, but since there's another force acting on the vertical plane, you add it.
Good. That was the thing I was wanting to say without saying it, so I'm pleased that you said it rather than me saying it. So yeah, if I just drew that diagram out again, which you might want to do, but this one's quite a simple one. You can see now, when we do our new diagram, that the value of R has changed. And that's often something that people forget in these kinds of questions. If the forces change, then the size of R is going to change. If the size of R changes, then the friction changes. So everything changes. As soon as R changes, everything else is going to change. So that's really why I've put this question in here. So the first thing we would want to work out is that R is equal to 8G minus P sine 60. You can see here, R plus P sine 60 equals 8G. So R is equal to 8G minus P sine 60. So now I can say, because it's still in limiting equilibrium, that P cos 60 is equal to mu R. Mu in this question is 0.5. So I might just take it a bit more slowly there. So I've got 0.5 R. So P cos 60 is equal to 0.5 times by 8G minus P sine 60. So we've now got an equation that can be solved because everything is just in terms of P. So I'll expand the brackets. What do I want to do to try and get P, find out what P is here? I could do, yeah. I don't necessarily want to do that. I'm actually going to isolate P onto one side and then factorize it. Okay, so I'm going to put this onto that side. So I get P cos 60 plus 0.5P sine 60 is equal to 4G. Then I factorize it, so I get P cos 60 plus 0.5 sine 60 is 4G. And so P is equal to 4G divided by cos 60 plus 0.5 sine 60. But yeah, Hamza, you're right, you could have found out what sine and cos were, and if that makes it a bit easier for you. So we'll just find out what P is now. So that's 4G divided by cos 60. I think we should get 42.0 newtons. So the maximum value of P has changed here. And the reason the maximum value of P has changed is two reasons. One of the reasons is P coming up at an angle changed the value of R, which changed the value of the friction. The other reason it's changed is because P is at an angle, some of the force is doing an upwards bit and some of it is doing an alongwards bit. So there's two kind of reasons why it's changed. It's very hard to predict whether the maximum value of P would increase or decrease. It probably depends on the angle that we have. So that's it on a flat surface. I think the next one is on a sloped surface, which is where things get a bit more interesting. And then I'm going to set you some questions for homework to do on this, okay? Can I go on to the next page?
Yes.
Do I have to do this? So, do I have to do this?
Yeah.
Well, I don't know a lot of this.
Okay, we'll see. We'll see.
Have you guys actually done some?
That's what I want to do.
We didn't do it in this much detail. Okay, we've done friction in further, haven't we? You probably won't get given a question like this, okay? You're probably going to get a question, well, sort of like this, but more likely some of these exam questions that I've got in here for us to have a look at in the next couple of lessons. So, we'll do this last one, and then that's bringing us to the close of our long double lesson today. Let's just read through what's happening. So a box of mass 10 kilograms rests in limiting equilibrium on a rough plane inclined at 20 degrees above the horizontal. Find the coefficient of friction between the box and the plane. So there's some really important features that we want to take from this. First of all, limiting equilibrium. What does that tell me about friction? It is at its maximum, so it's equal to mu r. The friction has reached its maximum. It means it's about to move, so the friction has reached that maximum value. Obviously, it's on a rough plane because we've got friction. So we can go straight into drawing our diagram now and thinking about what's going to happen. So we've got inclined at an angle of 20 degrees, and it's 10 kilograms. So I want to go straight in with my 10G. I want to go with my normal reaction. If it's in limiting equilibrium, which direction do we think the friction is going to go? It's got to go up the slope because it's a slope. It's going to try and slide down. So obviously, the friction is going to be going up the slope here. So we've got mu r. So this first part should be all right. Better get on with doing some of those force resolving though. So I'm going to split the 10G into these two, with that angle at the top as 20. This one running along here is which one, Ronak? It's 10G cos 20, and so I have 10G sine 20 running along here. You might like to draw out another diagram. You don't have to draw out this other diagram. If it's a complicated question, I would highly recommend it. And now that looks like a simple kind of scenario because of this word, equilibrium. So what do I know? Muhi, what do I know from this diagram?
Since it's a limiting equilibrium,
Yep.
shouldn't 10G sine 20 equal mu r?
Yep, and what else?
Oh,
Those two are equal to each other as well.
oh that, oh.
Yep, so those are equal and those are equal. So if I resolve in that kind of direction, I just get that r is equal to 10G cos 20. You get a mark for doing that, okay? You do get a mark just for actually writing these things out. Then if we resolve it along the slope, we can see that 10G sine 20 equals mu r, and r is 10G cos 20. So what is mu equal to? No calculators allowed. Tan 20.
On the 10G sine that.
Yes, Ekram.
Well, the value for me is quite big.
Yeah, what is tan 20? No, that's okay. Tan 20 is 0.36, so that's good. Maybe you're in radians mode. Yeah, in radians mode it's 2.23, which is pretty rough. But in degrees it's good. Yeah, but in degrees it's 0.364 to three significant figures. So part A is nice and easy. Now here's the interesting part, okay?
Find the maximum value of P.
And this is, Rayhan, this is the most important part of the whole lesson, because this is pulling together some of the ideas of thinking about the situation rather than just doing the maths. You have to think about what this looks like and what is about to happen in order to understand where you put the forces properly. A horizontal force of magnitude p newtons is applied to the box, given that the box remains in equilibrium. Okay, we want to find out the maximum possible value of p. So someone is going to take a horizontal force to this box. Now, if they took this horizontal force in this direction here, what would happen if they pulled it in this direction?
So go flying down.
It's gonna. Well, here it was on the point of moving. If you start pulling it in the direction we thought it was going to move in, it's going to start moving. So it cannot be acting in that direction. It has to be going.
Why do we not want it to move?
Because it says here, given that the box remains in equilibrium. So it can't be going to the left. It has to be going to the right. So you've got to stop and you've got to think to yourself. But I'm actually not going to even leave it on this diagram, okay? I know it's going to be going to the right. There's people that are talking when I've said this is the most important part of the whole lesson on friction. So I find it strange that people talk over bits that I've said are important. So I'm going to draw this second diagram because it's not as simple as you might think. Okay, so I'm going to just put on R, and I'm going to put on 10G, and we've just said that the pushing force has to be going in that direction, because if it was going in the opposite direction, it would immediately be moving. We know this is 20, and so I know this is 20. Now, we have been asked about the maximum possible value that P can be. Now, I want you to imagine, not necessarily being the block this time, I want you to imagine being the pushing force. There's a block on a slope, and you are pushing it as much as you possibly can so that it doesn't move. If you pushed it any harder, what would happen to the block? It would move up. Okay, if it moves up, tell me something else. What would happen if something is about to move up the slope, Ekram? Friction would now be acting down the slope. So you cannot just go to this previous diagram and add in P, because friction is going up the slope. It doesn't make sense. You have to pause and you have to think to yourself, well, if I'm interested in P being as big as possible, it's going to start moving up the slope, just about to start moving up the slope. So you need to say to yourself, if it's going to start moving up the slope, well, then there's definitely going to be, and it's hard to add this onto the diagram, there's going to be the friction would be going down the slope. So you need to make sure that you've written now friction. You don't have to write this down in the exam, but for your notes, friction changes direction because it will be on the point of slipping up. Previously, it was on the point of slipping down. It's now on the point of slipping up. I guarantee you will all do a question like this, and you will just be like, oh, great, I'll just add it in. You have to pause, and you have to think about what's happening here, because the direction of the friction changes according to what's going on. So there it is. That friction has changed direction from here. That's a terrible highlighter colour to use. It's changed direction from here to here.
Wait, so how would that affect the overall, as in like?
Well, because P is now allowed to be quite big, because it's got something that it's going against. If the friction was on the other side, P wouldn't be allowed to be its maximum. We're wanting to say that P is its maximum possible value. So you're trying to say, I want that force pushing to get as big as possible. And in order for it to be as big as possible, if you made it any bigger, it would start moving up, which means the friction is down. So we've got just a few minutes for me to do this next bit again. Well, these bits are going to be the same. You're still going to have this and this the same. But this P, you're going to have this force and this force here. You've got your P sine 20, your P cos 20. You can see how these diagrams get very, very busy. So let's draw this again. Going up is R. Going to the right is P cos 20. Going down is P sine 20. And 10G cos 20. I've been lazy and didn't do them on there. I've then got 10G sine 20. And I've got mu R. So it's a hell of a lot more complicated, and this is why the second diagram is there to help us out. So we're trying to find out what P is. Best thing to do is this one first of all. So resolving in that direction, R equals 10G cos 20 plus P sine 20. If we resolve along the slope, we should get P cos 20 equals 10G sine 20 plus mu R. Will mu be the same as earlier on in the question, or will it have changed? It should be the same, because mu is dependent on the box and the surface. We've not switched to a new box, we've not switched to a new surface, so mu will remain tan 20, and tan 20 is an easier value to use there. So I can substitute R in here. P cos 20 equals 10G sine 20 plus mu, which is tan 20, multiplied by 10G cos 20 plus P sine 20. Sorry, I ran out of space on that line. I'll write it like this instead. And then that's just an equation. You just have to find out what P is. So let's just finish this off. What's tan 20 times cos 20? So you get 10G sine 20, and then here you've got P sine 20 tan 20. Move it over and factorise. So you get P, let's try and save a bit of time, cos 20 minus sine 20 tan 20 equals 20G 20G sine 20. So P is equal to that divided by that. How much? 82.23. Great, so I'm just going to go 82.2 newtons to 3 significant figures. So it can be pretty big. It can be pretty big. And that's because it's taking into account the fact that it's switching directions that we have there. Okay, so I'm going to set you some questions on this for homework. I'm going to ask you to do exercise 7C, which is from this booklet here, from the Mechanics Pure 2. Not Pure 2, Mechanics Applied 2. I'm going to ask you to do the odd questions from exercise 7C for Thursday's lesson. So you've got a whole week to do it. If you find them hard, you might want to do some of the early even questions as well. And I'm sorry that took quite a bit longer, but we'll stop.